Okay, well, I'm going to go ahead and get ready to get started. And as people join in, they join in. But I'm going to do what I promised, and everybody else can do their thing. Um, and again, I am recording this. I did start the recording so that you guys would have it to use at other times if you would like to. Um, But anyways, with that being said, I'll go ahead and get started. I'm going to go ahead and let you first see a little bit of video here that I'll share with you. Everybody, oops, can everybody see that? I know you don't normally get to see from my side because you know how much I love being in pictures. So anyways, if you start over here on the far side, this is where we have our incoming power from the wall. So our incoming power, first thing that the incoming power interacts with is the circuit breakers that are on our control panel. Okay, so if the circuit breakers are off, what that does in effect is open the circuit, like you see up here, where you see that break in the circuit. That's an opening, and that means that the power is off. If the circuit is open, there is no way for power to flow. If it is closed, then it is on, and that completes the circuit. So, and if you need to ask me something, you can stop, but if you kind of let me go through it and write down your stuff you want to ask about as I go along, that probably will go better. Next, what happens is you see in old equipment, you'll see a line monitor. What that does is basically is our visible meter of what the incoming power is at any given time. Again, on older equipment, this is something that we had. Now, very rarely do you actually have the monitor showing up on the equipment, but you still have the line compensation that is occurring. And what that does is we have incoming power. It can be in 110, 220, 440, any of those, any of those voltages. But what happens is because it comes from the power company, it fluctuates. And everybody knows that because when you're living in your house, you have times when you'll see your lights dim and brighten, that momentary flicker of power where it changes. Those are called brownouts. That's when the incoming power gets reduced, but it doesn't get cut off. And then it'll go back to normal. So we have those many, many times a day. And if we don't have any type of voltage compensation in our equipment, this would cause us to have very different X-rays being produced at different times. So anytime there was a decrease in the incoming power, our X-rays would appear underexposed, and anytime there was an increase in power, then we could have overexposed X-rays. So, because that voltage variation is about 5%. So that's a huge fluctuation and would make a big difference in our radiographs. And that would basically be that, one time your technique works and another time your technique doesn't work. And who would want to work in a world like that? That wouldn't work well for us. So that's what the line compensator does. And the line compensator, these taps, that's what they're called, these little lines with little dots at the end, they're called taps. They come off of the far side of the auto transformer. This whole line coming down, all these windings you see are all the auto transformer, and that's considered the very first part of our circuitry to get power to it. Okay. The auto transformer will vary the voltage and voltage and current, because when voltage is varied, the current is varied, okay, because they have an inverse relationship to each other. Okay, so that being said, if it varies the voltage to both our high voltage circuit and our filament circuit, okay, so it affects both circuits and basically provides the power to both. It has one set of windings and operates off of self-induction. So I'm going to go across the bottom side because that's what truly should make sense to you. This is the filament circuit coming across the bottom, and the whole point of the filament circuit is to provide the power to our X-ray tube to the filament to heat up the filament. That is the whole purpose of the filament circuit, okay? So that matters. It makes more sense that we deal with this first, because if we don't have enough heat to the filament, then we wouldn't be able to boil off electrons. We wouldn't have thermionic emission. So if the power is turned on to our X-ray circuitry, then the filament has power to it, okay? So the filament is always on as long as the X-ray equipment is on. That's not true of everything, so that's an important thing to pay attention to. So again, auto transformer is going to be what is going to supply the initial power to the filament circuit. That power is in AC, alternating current. That matters because everything up to and including your transformer, you always want to have in AC power. And once we get past these transformers, then we want to have direct current, because we don't want flow from anode to cathode. We only want flow from cathode to anode. So we have a couple of things that we see on our control panel that are part of this circuitry. We have our MA selector, and this generally will allow us to select our focal spot as well. Sometimes we can have separate focal spot selectors. And if you notice, this is a zigzag line on here. The importance of that is an MA selector is a variable resistor, okay? It is a rheostat. So if you think about different things you have in your house, if you have dimmer switches, if you on your oven, unless it's all digital, you know, when you turn your burners on your stove, have variable resistors because you can set it to different temperature levels. You know, you have low, medium, and high, and that can be represented by numbers. It doesn't matter. Just understand that as you turn that knob, you are changing the temperature to that specific burner. So that's what a variable resistor does, okay? And so it's our MA selector, and we can choose a low MA, anywhere in between to high MA, and these are the taps for that MA selector. Next part we have here, which now we've crossed the line into our high voltage side, because this is our primary circuit, and everything that's on our control panel controls this side. And this is all low voltage, because if we're touching it, we don't want to be touching high voltage. Okay, so this is a protection for us as technologists. So in here we have our filament transformer, okay, which is also referred to as our step-down transformer. So we knew we had incoming power, and let's just say our incoming power standard is 220. Again, it could be 110, it could be it could be 440. It doesn't really matter what that number specifically is, just that that's our incoming power and that it's in alternating current, because that's what power we have in the United States, is supplied in alternating current. Anything that I can plug into a wall is always going to rely on alternating current. If it operates off of batteries, that means that it needs direct current. Okay, so that's an easy way to kind of recognize between those two, whether something needs alternating current or needs direct current. Okay, so alternating current coming up to here. If you notice here, the windings, these are your windings on your primary side. So on this side, I have a whole lot of windings, and on this side, I have very few windings. That's why this is considered a step down, okay? So I said the incoming voltage was 220. This is a step down transformer, the filament transformer is, and the voltage gets stepped down from 220 volts to approximately 6 to 12 volts by this particular transformer, because what we need from this transformer is very high we need amperes, not milliamps. We need amperes to provide enough current to the filament to heat it up to the level that it will boil off electrons. Okay, so this transformer is what's responsible for getting that current to the level that's necessary to boil off the electrons. So that's for our filament current, okay? And our filament current, again, is in amperes. It's in about 3 to 6, and different parts of Bouchon will say 3 to 8, so just so you recognize. But we're talking amperes, okay? So this is a very large amount of electrons, okay? So amperes are very high. And again, we're talking about heating the filament to the level where we can boil off the electrons. So this also, we have these lines coming into the X-ray tube to the filament side that are, one goes to a small focal spot, the other to a large focal spot, and we're basically our filament current. We're also, if you notice, we have a connection to the high voltage circuit. So I want you to recognize that. So we have a primary circuit, a filament circuit, and the high voltage circuit. All three of these operate in tandem to provide, that make up the entire X-ray circuit. Okay, now I'm going to stop talking right this second and ask you if you have any questions to this point about that filament circuit and primary. So, questions for me? Okay. All right. Well, then I'll keep going. And like I said, this is just an overview to start with, and we'll get into more detail once we do this. So again, primary and filament, I have to have the filament heated up high enough to be able to provide thermionic emission, to provide the electrons that will be projected across the X-ray tube to interact with the anode to result in X-rays being produced, right? So that has to come first. And like I said, the filament circuit is always on. We always have filament current because we have to have current to the filament to keep it heated up. Because if we try to produce get to the level of thermionic emission without having that filament sitting at a level where it's already warm, we would just crack the filament, okay? Because we're just talking about a little tiny thin wire And that it would just break the filament, and that would be it. And your, $20,000 X-ray tube would be destroyed. So that'd be no good. Now, tube current is different. Okay, tube current is those actual projectile electrons that were boiled off and their flow from cathode to anode. That's actually our tube current. So it's important that you differentiate between filament current, which is in amperes, to tube current, those projectile electrons that are sent across, speeding across the tube at half the speed of light to crash into the anode and interact with the anode and actually produce X-rays. That's measured in milliamperes. Tube current only exists at the time of exposure. That's the only time we have tube current. So when I make a small adjustment in my filament current, say I went from 3 amperes to 3.5 amperes, that would represent just like millions of more projectile electrons available for tube current. So it only takes a little change in filament current to make a huge change, a large change in tube current. Okay, that's something you want to recognize, because again, that's measured in milliamperes, and we know 1 ampere is 1,000 milliamperes, right? So one number is a small number, one number is a big number. Okay, which presents a smaller number. So that gets us everything to this side of the tube, to the filament side of the tube, where we're going to be projecting across. Okay, so now we're going to go ahead and we're going to talk about what's going to be responsible and power that high voltage or secondary circuit. Okay, so again, we said up top we have major and minor kV taps that come off of this, the auto transformer. Okay, those major and minor kV taps, you don't, some of your equipment you have nowadays, you don't see that distinguishing between the major and minor, but when you're changing it like digitally, you'll have one set of buttons where you can make the changes incrementally, like 1 kV at a time, fine-tuning, and then you have your major where you're changing your kV 10 kV at a time. That would be your major kV selector. So major is like about 10 at a time, and minor is like 1 to 2 at a time. Usually you guys digitally would be 1 at a time. So next what we see is our KVP meter. That's important that you recognize to see that KVP meter on our circuit board. So at our control panel, we see the KVP meter. And you say, wow, we see a KVP meter, but you're telling me that this is only low voltage? How can that be that I see the KVP meter here if it represents kilovolts? It's actually, the KVP meter actually gives us the information in kilovolts, but that information is read by the, from the auto transformer and this primary side of our step up in volts, and then uses this turns ratio here, the turns secondary over turns primary, so turns secondary over turns primary, to tell us what kilovoltage will be at the time of exposure. Okay, so that's very important. This is called the pre-read meter. Okay, and the KVP meter, in this circuit we're talking about, it is a parallel circuit. It's connected in parallel. That means the voltage is constant, and that means if You can think of it kind of like a ladder, and if a rung is gone the ladder, you could still feasibly use the ladder. You just have to step over that particular rung. There's no rung there, so you have to step a step higher. Doesn't matter. Everything still works because the voltage stays constant. When we talk about series circuits, they're more like a circle. So say you have little pieces of rope tied together, and if you take one of those ropes apart that helped make up that complete circle, then you would no longer have that circle. You no longer get power because one portion of it isn't working. So you probably heard the thing like if like a cheap set of Christmas lights, if one light goes out, then in cheap set the whole strand doesn't work. So you got to sit there and figure out what the heck light is messed up, or you just throw them away because they're cheap anyways. If you have the more expensive Christmas lights and one light goes out, then that light's out and all the rest of them are still working. So at that point, what you do is you're like, okay, that's the one that's out. I shut it off, and I pull it out, I replace it, and voila, it's working again. So those are connected in a parallel circuit. So everything else continues to work except for that one bad bulb. So that gives you a little explanation of how this one parallel and this one is in a series. Okay, your ammeter. All right, so this is your step up transformer. Okay, so what happens, we go from volts on this side to kilovolts on this side. So our 220 incoming voltage can be varied on this side, and it will affect what we have on this side based on the turns ratio. So we're going to have kilovolts on this side. Both the step up and step down transformers both work off of mutual induction, whereas we said our auto transformer works off of self-induction. So these work off of mutual induction, which basically is a use of the varying your current and voltage induces a magnetic field. The magnetic field induces a higher on that secondary side. So yeah, we have electromagnetic radiation. Interesting, huh? So we're creating electromagnetic energy here. So here we have our rectifiers, okay, rectification bridges all along here. If you notice, we have lines that run here and run completely down and around, okay? So this secondary side is our high voltage side, okay? And this power from this secondary side is fed into and through the X-ray tube and back out to that secondary side again. That's important. Question, Chanel?
Yeah, I think also what would help me is if you showed me where all of those components are in the lab, like where the circuitry runs through.
Sure.
So you can show me tomorrow.
Sure.
Okay, thank you.
Yeah, that'll actually be fun. Sure. Okay. So anyway, so here, rectification bridges. What's happening with these rectification bridges are we are taking, remember we had AC current because we got our current from the electric company. So we had alternating current, and we know that this X-ray tube has to have direct current. It can only have electron flow from filament to anode. If we had backward flow, that would be horrible, right? We would that would be catastrophic to the X-ray tube. That'd be no good. So these rectification bridges stop that backward flow. So when, say, B and D are working together and A and C are working together, they can ask you questions about that. Honest to God, I think they've kind of gone away from it because it's just not that. Just understand that rectifiers stop that backward flow or that negative flow, okay? And that's what we needed to do. That symbol here of the 3 lines, each getting a little bigger, that's the symbol for ground. One of the most important things that you guys need to recognize from this drawing is the different symbols that we have. So that's the symbol for the variable resistor, the squiggly line, a transformer, going to be a different number of coils on one side to the other. So if it's stepped down, it has more coils on the primary side than it does on the secondary side. If it's step up, it has more coils on the primary side than it does on the less coils on the primary side than it does on the secondary side. Rectifiers will be an arrow pointing into a line. That's a symbol for a rectifier. Symbol for ground. Any meter, they're not going to tell you the name of the meter like I did. They're just have a circle with an arrow in it. That's for a meter. Yes, Chanel?
Can you repeat the step up and step down again for me?
Sure, hon. This one's a step up, right? So I have fewer coils on the primary side than I do on the secondary side. And when we say step up, we're saying we're stepping up the voltage, okay? So the name of the transformers, when we say step up or step down, that's related to voltage. So step down transformer or filament transformer, we have more windings on the primary side than we do on the secondary side because the voltage is being stepped down from that 220 down to like 6 to 12 volts. So what a car battery would provide.
So why is it being stepped down on the cathode side?
Well, it's being stepped down on the filament transformer because we need a large amount of current. So we need to have that huge electron flow coming to heat up the filament.
Okay.
So current is about the number of electrons, and voltage is about the force, the applied power, the applied energy to push those electrons. Okay, so we need low voltage at the filament, and we need high voltage to attract the electrons from cathode to anode.
Gotcha. Thank you.
You're welcome. Okay, what else am I not telling you here? Okay, you guys all know I don't have to go into a lot about the tube. You have your stators on the outside and your rotor on the inside, and that's based on electromagnetic induction. The stators there's sequence, the magnetic field is moved, and it's moved in sequence, which causes the rotor to start turning because it wants to be in alignment with that magnetic field. So if it's a constantly changing magnetic field, then it's chasing that magnetic field. Let's see. And our MA meter, that's actually a pretty interesting meter. And if you can notice this little weird configuration here for the MA meter, and that it's hooked up right to the center part of the secondary side of the step up transformer. That is at a 0 voltage point. That's important because although it's being measured over here on the high voltage side, we actually have an MA meter that appears on our control console, right? And if you ever paid attention to it when you were making exposures in that room, if you guys, I think you guys got to, when you make exposures in that room, what happens is that's the only, at the very moment of exposure is when you get that information from that MA meter to your control console. Okay, but so that's important that it's linked right to a 0 voltage point, because we wouldn't want information from high voltage on something that should only be low voltage to protect us. Okay, so now I'm gonna flip you off of me. Oh, that sounded good. No, I won't flip you off, sorry, but I'm gonna change where what I'm focusing on and try to give you some info here. There we go. Sorry, having to flip everything around so I can come back to my screen. Okay, so what I did here was I kind of gave you a couple different drawings that have the information for us on the X-ray circuit. I have a couple different ones that give you the information in a little bit different format and all, but I thought, well, that's helpful because we never know if the registry is going to use, you know, Bashong drawing or a Carlton drawing or a Selman drawing, as long as it is something that's represented in one of the approved texts, it could be used, right? So that's why the symbols are important. Okay, so this one I pulled up. I thought it was a pretty good one just because A, wasn't one that I thought that you'd probably seen, but B, it's just using the symbols. So I thought it was a good way to kind of go through this. So this A shows you that incoming power, right? And it's a sinusoidal wave. So that sinusoidal wave means that it's alternating current, okay? So here it shows you, okay, coming into our circuit breakers, and you see how we have that little line up there that breaks the power chain from point A to point B, right? See, it's up in the air instead of connected to this second one to provide that circuit. So that would show you that the circuit was open, and so I didn't have incoming power to it. So it's an important thing to recognize. And then you come down here and you have your taps. And of course, they did a lot better drawing than I did because, you know, mine was me drawing and I'm not an artist. So here's our taps for our line voltage compensation. Okay. And this is our auto transformer with just the single windings. We know it works off of self-induction. So that means that that single winding induces and varies the voltage and current that it's supplying to the secondary circuit and to the filament circuit. So here's our taps for major and minor KVP. Okay. And this meter here, what meter is this one?
The KVP meter?
That is correct. Yep. And you just have to know what the meters are by where they're located in your circuitry. Because remember, I told you they just show you that with the arrow in it. That represents a meter. So it could have been here. It could have been over here. If it was over here, it would have been what meter?
MA.
Correct. Okay. And this at E, and I think I didn't even bother talking about this. This is our timer circuit up here. So that's where, we know in our control console, we can adjust the time depending on what type of timer we have. Will depend on how we adjust the time. We have digital or electronic timers, which are most common now. They're the best. What we have in room 1 is a synchronous timer. Everything's based on that 1/60th of a second. So it's not the best timer because the shortest time you could possibly set would result in like a 17 millisecond exposure. Okay, so then here we come up to the step up transformer. And like I said, you see how much fewer windings on this primary side than you see on this secondary side. And we also, that's where we have the transformer law comes in, where we have that NS over NP, so turns ratio, times VS over VP, which is voltage secondary over voltage primary. And you guys have probably seen questions on your RAD review that say, basically are asking you if the primary side is supplied with 220 volts and the turns ratio is, yeah, who knows, 20, or no, say, 100 over 1, what would be the secondary voltage? So basically you should be recognizing that they're talking about a step up. You always want to know how the story's going to end. That's what I always tell you guys about word problems, is when you're reading it, you want to read the story, you want to find out what they're talking about, and so that you know in advance what's going to happen. You may not know the exact number you're going to get, but you know what to expect. So since you guys are probably more familiar with inverse square law, I'll talk to you in relation to that and say we know that if we increase the distance, that the intensity is decreased, right? Because we know that the X-ray beam diverges, and so less of those X-rays would hit a specific area. So if you're reading a problem and you see that the distance has been increased, well, in your mind, you say, oh, the distance got increased. That's a good thing, because that means that the quantity of X-rays was decreased. So that patient's dose was decreased, or that RT dose was decreased because they got further away from the primary beam. So that's how when you're looking at transformer law problems, the same thing. You have to be able to read them and see, if this is a step up transformer, then I expect the voltage to be higher on the secondary side than on the primary side. By the same token, if that voltage goes up on the secondary side, the current is going to be decreased on that secondary side. And that's important to recognize, because step-up transformers increase voltage. So if voltage goes up, current has to go down, okay, because they work in tandem. So if a second part of that question asks you about the current, you would know that to follow up on that current was going to be decreased because the voltage was increased. So down here, we have the filament transformer, or the step down. And you see how we have lots of windings on the primary side and very few windings on the secondary side. So we know that means that the voltage is going to be reduced on this one. So if the voltage got reduced, what happens to the current?
It increases.
Yes, it does. The current would be increased, and we know that's true, right? Because we know the voltage went from that incoming 220 down to 6 to 12 volts, and we know that we went from milliamperes to amperes. So big increase, right? And here we went from that low level incoming amperes down to milliamperes on the secondary side of this one. So what do these symbols mean? What do they stand for? Oh, no takers? These are rectifiers. Okay, so the arrow with the solid line basically showing you impedance, that means it's stopping the flow at that point. So that's the key, because we're trying to change this AC current cycle has to be switched to DC because this is going into our X-ray tube. Okay. So even though it's kind of showing you this looks a little skewed, this is our filament side, this is our target, so negative and positive side.
I was wondering what that was.
Yeah, that's supposed to, hey, if I was going to have to draw an X-ray tube, I'd rather draw it like that than try to draw a nice one like Miss Menzel does. She kills me on that. She draws it, now I can't draw. And then down here, what's this?
Some type of selector?
It is, yep, that's our MA selector, yep. And that is a variable resistor, right? That's why we have these little squiggly lines. It's a variable resistor or a rheostat. So any of those answers, so if they give you multiple names for the same thing, you still want to recognize it as what part it actually is. And that's how they're going to show you. You're going to have to recognize these symbols. So if you see just one set of windings, you know, and because of the location, you know, auto transformer gets power first, operates off of self-induction. I go over here, MA selector, you know, here, this is a step down transformer. Where does it belong? In my filament circuit. This is a step up transformer. This is my high voltage transformer. It steps up from primary to secondary. So you have to recognize by number of windings what it does. These are symbols for rectifiers. Over here, a symbol for a circuit breaker. Incoming power, AC power. Okay, so just recognizing those symbols. And let's see. This one you should recognize, although for whatever reason it came out blurry, but this is the one that's out of Bouchon. And again, just recognizing the symbols. I'm sorry, I can't make it come in any clearer. But just recognizing the symbols and recognizing meters. So where's the meter located? That's what tells me which one it is. Rectifiers. Now you got an X-ray tube that looks like an X-ray tube, right? Step up, few windings on the primary, lots of winding on the secondary. Step down, multiple windings on the primary, few windings on the secondary. Auto transformer, one set of windings. Taps for your major, minor. KVP meter, pre-read, doesn't read it in kV, gives you the number in kV, but reads in voltage. And your incoming power. And this last one I actually thought was a really good one because it kind of shows you that whole how each section, because this is real basic, I mean, like super duper baby schematics for what our X-ray circuitry actually is. But it's all that we have to know. So, you know, as technologists, it's what we're responsible for knowing. So we don't have to rebuild the equipment, right? Thank you, Jesus. But we have to at least understand it. So this one, I love this diagram. I hadn't seen it before, but I was like, ooh, I absolutely am in love with this. So it shows you, here's everything that's on our control panel, right? So I have my auto transformer, and then I have my KVP meter. I have my timer control, and then here's my primary side of my step up transformer, low rectification bridge here, and then the little symbol for the rectifier. And then down here, my MA selector, and then my filament transformer, my step down. More windings on primary than there are on secondary. And then, oh good, this one does, Pilar? Good, good. Yes, you know.
Okay, so for the high voltage components, the step up transformer is like kind of in the middle. So which side is it on?
Well, the high voltage transformer is on the high voltage side. So the primary side of it, and if you look, if I flip back, let me flip back real quick so I can show you.
Uh-huh.
Here, you see how where in Bouchon's drawing, he puts it all, so both transformers end up in the high voltage section, and that's important to recognize because they both are about exceedingly high voltage or current. So sometimes they can separate this one between the primary and secondary side, saying, this is low voltage on this side and this is high voltage on this side. But they're all contained within the high voltage generator. So that, to me, that tells you something, right?
Right.
So they should all be contained in this high voltage section.
Gotcha. Thank you.
Oh, that's okay. So on this one, what they tried to do was, you see how they put the line here and kind of tried to draw it into the high voltage components. So they probably just could have gone over a little more so that it made more sense to you. But yep, so all these are in high voltage part. And then the last but not least, just showing this connection from, because what happens is, even though the filament gets its gets the current supplied to it from the filament transformer, right? So voltage and current run in tandem. Voltage is that push that the electrons need to move, because electrons exist, right? So they just exist. Voltage pushes them. You can call it the push, you can call it the pull, however you want to think of it, but it's what provides the energy to move them. That's why we call voltage potential energy, because it's that push that's needed to move the electrons, cause the electrons to flow. Okay, so once we get the electrons, then we boil off the electrons at the filament, right? Because the filament has to be heated up. Then electrons are boiled off. They travel across. They interact with the anode. We know that a bunch of them will produce X-rays, right? But we know that some of them aren't going to. That's the nature of the beast. Some of them are not going to. And those electrons are going to have to continue through the circuit, and they're going to have to be fed through that circuit, and they come back around and into this secondary side of the high voltage transformer to basically be reused. They're recycled all the time. Okay, so that's what actually completes that full circuit, is that ability of those electrons to go through, because if we didn't have a completed circuit, we would not be able to have flow. We wouldn't have current flow. You always have to have a closed circuit. So we have 3 closed circuits that are interconnected with each other. Okay, everybody feel okay right at this moment?
Yes.
Okay. So let's talk a little bit about some of the details. Okay, so some of the things that we do, some of the different components and what they do. We'll get more technical about the information and see if hopefully we really get it. Well, that's a good thing. Okay, so I'm not going to go through the tables and all that stuff. That's just silliness. All the stuff we control at the control console, you guys know what stuff we can choose. You know that we control the quantity and the quality of the X-ray beam, right? All from our lovely little control console. You know that we can pick where we're going to make the exposure at, if we're using the table bucky, the wall bucky, the tabletop, whatever. We have control of that. If we have AEC, then we have control of the cell selection. And we can choose our kV that we want to use, even though there's one that's already programmed into it for whatever part we're doing. But we can manipulate the kVp, and we can manipulate the MA. We can set a backup time, but we do not control the time of the exposure. Okay, so that's something important to recognize about AEC, is I have no control over the time of the exposure. It's once enough, basically enough X-rays have reached the chambers that will cause it to shut off, or if we have reached our maximum time, or a backup time where it would shut off. Those two things would cause it to shut off, but we don't. As RTs, what do? We initiate the exposure, whether we have a 2-stage switch, considered a dead man switch, or whether we have a separate rotor and exposure switch like we do in the back room in room 2. But we control the initiation of the exposure, but the timer circuitry or AEC, depending on which one you're using, is what will terminate that exposure. Because if you think about the time of exposure, you know that we couldn't shut it off in time. It goes by too fast. Okay, so let's talk about the individual components. Does anybody remember what, and I'll go ahead and flip back to that image and maybe it'll help too. Does anybody remember what the job of the auto transformer is and some special stuff about it? That's a whole lot of crickets, guys. Yes, self-induction. Good, thank you. It operates off of self-induction. How many windings does it have?
A lot.
It does, but it has a single set, right?
Oh.
Single set
Yes.
of windings. Yep. And whereas our step ups and step down have 2 sets of windings. Okay, so single set of windings. Okay, so good. And what is that auto transformer other than being the first thing that receives power? What is that auto transformer responsible for doing for the entire circuit?
It provides the current. I don't know if it's like the right word, but like to the filament circuit and high voltage.
Okay, yeah. So it supplies a precise voltage to both the filament circuit and to the high voltage circuit. Very good. Okay. So that's what its job is for us. Okay. It takes that incoming power and it varies it as needed for the step up and the step down transformer. So that's a really important job. Okay. What part of our technique selection is responsible for the quantity of electrons that we produce?
The step down.
Oh, wow, I love that you said that because you got real technical, and that's good. Yes, the step down, but what we're basically saying is when we set the MA on time at the control console, we're actually stating the quantity of projectile electrons that we want to travel from cathode to anode. Okay, so that would be our mass value would be that specific number that we were telling it that we wanted produced. Okay, so kV, when we choose a specific kV, what does the kV control? Yes. And it does control the quality, and the quality is the energy. Okay, the quality is the energy of the beam. Okay, so potential energy, ooh, that sounds like kV, voltage to me. Okay, so it's the quality, the penetrability, the energy of the X-rays that we're going to produce. Because what you have to understand is that those projectile electrons, we know that going across the tube, they're going to go across the tube at half the speed of light. That's what they say. You know, sometimes you're like, man-made, wow, how can that happen? But it's supposed to be about at half the speed of light. But the kV is actually our measurement of the energy of the X-rays that we produce. Okay, so we say like 69 kV X-ray or 70 kVp X-ray, but that's the peak energy of that beam. Okay, so and also kV is also to some degree responsible for quantity, or will affect quantity only in as much as if we pick a high enough kV so that all the electrons that were boiled off at the filament in thermionic emission, so that whole little cloud of electrons, if we don't use a high enough kV, we can't get all those electrons across to interact at the anode. So we have to have a sufficient kV to pull all the available electrons across. But that's the only way that it ever affects quantity, is that ability to bring everything that's available there across. And if I use too low a kV, some of those electrons will just be left sitting at the filament. Okay, so that's the only impact on quantity that kV has. Everybody okay with that so far? Okay.
Yes.
All right. Okay. So does anybody remember what I told you was actual tube current? When do I have it and what is it?
Can you repeat that?
Tube current. When do I have tube current? And what is tube current?
Oh, tube current. When
Hmm.
electrons flow to the anode side.
Okay, so very good. Okay, so tube current is first we have filament current, right, that boils off all those electrons. Now those electrons are available,
Mhm.
and when I actually hit the exposure, or if I have a two-stage switch, when it's rotored up and the exposure gets made, at that time of exposure is the only time that I have tube current, and that's that pulling of all of those electrons that are there, trying to drive them across from cathode to anode. That's when I have tube current. So that voltage at that very last second, that high voltage is applied, make that anode very attractive so that all those electrons can be pulled across to interact with the target. So just at that time of exposure do I have that tube current. And we designated what that tube current would be by setting our MA and time. Does that make sense to you?
Yes.
Okay. All right, good. So tell me what my step-down transformer does for me.
The step down transformer provides the current for
What current?
electrons. The
What current?
filament circuit current stuff on that side.
Good. Yes, yep, it provides filament current, so it heats up the filament, right? Okay, so what happened to my incoming voltage with a step down transformer? What happened to that incoming 220 volts?
It goes down.
Okay, yes, it does. Do you remember that number or the range that it goes down to?
No.
Okay, goes down to 6 to 12. And so if the voltage went down, what went up?
If the voltage goes down, the current goes up.
Yes, very good. Yay. Oh, that makes me so happy because let me tell you, I can't even tell you sometimes how hard that idea is to get across. It's like if one's going up, the other one's going down. You can only push so many through at a time. So you have to always think, if you had, I was thinking about this morning and I thought, oh my gosh, social distancing is such a good way to explain this. If you had all your think of all your electrons as students. Okay, so we have 14 students in our class. I know that's hard to believe when we only see you guys 7 at a time, right? But there's 14, you guys have 14 of you in your class. So if I lined you all up in a line and you were social distanced and everybody's just walking at the same pace, it would take you more time to get out the door than it would if everybody was just walking out like a normal group, right? How you guys used to walk out down the hallway where everybody was all kind of mushed in together going down the hallway. More of you would get through, but then when you hit those doorways, that was an area, like think of that like a resistor, so when it impeded the progress, so you had to, if four of you were walking across the hall and going down, you had to reduce your number down to one or two to go through that doorway, right? So that meant that that flow was restricted there. So we talk about what when we talk about like Ohm's law, and we say, okay, voltage is the product of current and resistance. So only so many electrons can flow at any given time based on like the diameter of the wire and stuff like that. You guys remember Ohm's law? None of my crickets remember Ohm's law. Did everybody jump offline on me?
No, I'm still here. I don't remember though.
Okay. It was just funny. I was just like, okay, nobody's going to answer me. Okay. So, Ohm's law, let me see. Go here. And I'll write it down and see if you actually remember it. Remember that formula?
No.
Nope. Okay. All right. What this formula says is voltage equals current times resistance. And that's literally what I was explaining to you when everybody got like oh so quiet on me. That's what I was explaining to you about you guys going down the hallway. If you were all going down single file and you were all 6 feet apart, how long would it take 14 of you to get through the doorways and get out of the building versus if we were traveling pre-coronavirus when everybody just kind of a big old group going out of the classroom, and the only thing that ever impeded your flow or caused resistance was when you had to get through those little doorways like down by the auditorium. You remember that doorway where it narrows, and so only like one or two people could fit through at a time?
Yes.
Oh, okay. And that's why I'm saying that's what we call resistance, because resistance impedes the flow of electrons. So it's like letting fewer through, because if you think of it like a doorway impedes the flow of people, right? If we're walking down a hallway and the hallway is 6 foot wide, a lot more people can fit down that hallway. When you hit a doorway that's only 3 foot wide, that just cut the flow of people basically in half or more to go through it at that point. So that's a representation of the Ohm's law. Okay, so remind me, I want to talk to you guys more about Ohm's law, because you're going to be seeing this and you'll be like, what does that mean? And that's voltage equals current times resistance. So that's when we talk about the diameter of the wire and stuff like that. Okay, so I'm going to go on, just go back to something a little less strenuous, hopefully. Exposure timers. Exposure timers are the different timers that are used on our equipment to manage the time, terminate the exposure. Okay, so we have several different types of exposure timers. We have electronic timers, like we have in room 2. They're the most accurate. They're obviously very sophisticated. That's what you guys have on the majority of your equipment that you guys are using now. But they're the most accurate, and the wonderful thing about them is that they can allow an exposure as low as 1 millisecond. That's real short time. Obviously, us as humans could never stop an exposure at 1 millisecond. That, we don't have that kind of reaction time. Okay. So that's a really good thing that allows us to use higher MA and shorter exposure times, which would mean that we should have less motion. Okay, so that's a good thing. What we have in room 1 at the school is a synchronous timer. And so that's based on a system of 60 rotations per second. Okay, so basically single phase. And so the shortest time you could set that to would be 1/60th of a second. And 1/60th of a second is 17 milliseconds. Okay, so that would be the shortest exposure that we could possibly use on that system. And so you can see the benefit of those electronic timers. They're much better. I don't know if any of you guys saw this out at sites, but some equipment you have that use mass timers. So instead of setting the MA and the time, you actually set the mass on that equipment. Did any of you guys see that on any portables or anything like that out on site?
I think so.
Oh, okay, okay. Because some portables will have it. CFR had one a real long time ago. But usually what they do is they're set for a falling load where they use the highest MA and the shortest time to make that specific mass. So all you would do is say you wanted to use 20 mass. You don't set your MA and time to get that 20 mass like we do in room 1. You just set 20 mass.
Yeah,
So
on the older portables, it was like that.
okay, real good. So at least you got to see it. But that's how that works. And then our other type of exposure, our other type of exposure timer that a bunch of you guys are very familiar with is using AEC. How many people are familiar with that? Bunches, I'm sure. Yeah. Okay, so AEC. AEC is not a bad thing. I know that there's a lot of different opinions on AEC, and a lot of people think that AEC makes lazy techs, and I say lazy people make lazy techs. AEC does not make a lazy tech. What you can do when you have AEC that would show that you are not a lazy tech would be adjusting KV on that equipment, because unfortunately people other than RTs program the equipment when the equipment is first installed, and the equipment is still set to film screen techniques. Well, we haven't used film screen techniques in years. Okay, so there's no reason in this world that our systems should be still set to film screen techniques, other than the fact that the equipment's not set up by RTs. So the people that are manufacturing, and then they got their little people programming this information in the equipment, they're just programming in the same old stuff that they've been programming in for years. Okay, so keep that thought in mind. So if you as an RT, one of the major components of your code of ethics is about patient protection. The guiding principles of our code of ethics all revolve around patient protection. So one of the best ways that we can protect our patients is by limiting the dose to the patient. Okay, so that means I want to be, I want to be good. I want to know what I'm X-raying, and I want to know my anatomy well enough that I can, collimate, to the area of interest. But I need to understand the physics behind X-rays so that I can say, oh, this says 70 kV. I know I can use at least 80 kV on this part. Heck, I know I can even use 90. But if it's set at 70 and there are some lazy techs around here and I'm seeing that, then let me at least go to 80, use the 15% rule, and then I know that whatever mass I get using AEC will be half of what everybody else is exposing their patients to. Now, is that a perfect world? I say no, because we can tweak it even more, but it's a good start. Okay, and if you guys do that and just take the time to go, oh, wait a minute, this says 70, I know I can at least use it, go up, use your 15% rule and go up 10 kV on whatever you're using AEC on, so that each of those images reflect half the mass of what your average person that's just walking up to that equipment and just making the exposure using AEC, making no changes, is going to expose their patients to. Does that make sense to you?
Yes.
Okay. And I hope you guys do that. Okay. I hope you do that when you go back out there this time. You can show me good traits of people that want to be strong techs. Okay, so we got a few problems with AEC, okay? Because, oh, go ahead, Amy, you have a question for me?
Yeah, I was just gonna ask, like, in the site that I was in, they just went by like the exposure indicator, like they just made sure that it was under like 400, so between like 200 and 400. Um,
Hmm.
and they didn't really like play around with the technique. So, like, what my question is, like, what really is the exposure indicator? Is that like how much the patient's getting, or?
Well, yes, and here's the thing, is it's really not so much how much the patient's getting, because we can actually measure the patient's dose now with the equipment that we have, and we can see the exact dose that they're getting per exposure. But what that exposure indicator does is basically measure the exposure to the imaging plate. So a couple things can affect that. Remember when I told you about that, like the imaging plates now don't like only a small area being exposed?
Yes.
Because they can't read that really well. So that can set your exposure, your EI numbers off by collimating down really small to a real small section of your imaging plate. So you have to, nowadays you have to have, like, at least, if it's digital, that it wants almost half of the plate being exposed. So you've got some ways you can control that. At some places you have where you can, even though you're not really changing the size of that detector, you're changing the size of the area that you'll be exposing. I know for a fact Orman has that ability where they can pick like a 10 by 12 area for exposure of that 16 by 16, and then it registers the EI numbers properly again.
Oh,
But not all places have that. But the other thing that you can do is to get the right EI numbers, but have less radiation dose to your patients is increase the kV, go up 10 kV, and then it'll reduce the mass by half, but your EI number will still be the same.
Gotcha. That makes sense. Thank you.
Yeah. So, I mean, that's something, how simple is that to do? You know, I mean, it's literally going bink. Okay, it's up 10 kV. Wow, God, that was so much stress on my body to do that, right? But that's just like one simple thing that we can do that changes the, it changes the whole thing of what's happening to that patient. That patient's getting such a small exposure that way, a much smaller exposure. Okay. All right, so again, AEC again, that doesn't make, it doesn't make lazy techs. Lazy people make lazy techs. If you don't collimate because you're like, oh, it collimates. I got PBL. It collimates to the size of the IR, so I don't need to collimate more than that. That represents more exposure to your patient. So there's a lot of things that we do if we get lazy that result in higher exposure to our patients. But I will tell you that every time you renew your ART certification, you re-sign your code of ethics. So just keep that thought in mind, that code of ethics is all about protecting our patients, educating our patients, and educating people around us. Okay, because we are the ones that they have direct contact with, that have the most information about what radiation does. So we can educate them. Okay, so AEC does have a few problems with it. If something goes wrong in AEC and you go with the factory setup, then basically your exposure will terminate once it reaches 600 mass. Okay, that's if something goes wrong. Well, things go wrong with equipment. Okay, so that happens more often than you think, unfortunately. So if you don't adjust your backup time, then somebody's grandma just got exposed to 600 mass because the equipment malfunctioned. Whereas if you paid attention and you said, oh, okay, my gosh, she's so little and frail, and I think the most I need for doing that pelvis is going to be 10 mass. And I say, well, gosh, I don't want to figure out what 1.5 times that 10 mass is, because that seems like too much work. What's 150% of 10? Oh, I don't know. I'm having a bad math day. Okay, if you're having a bad math day or a bad math life, say, what is double that? And that will be 20, right? Go with that 20 mass. If something goes wrong with your equipment, your exposure terminates at 20 mass. If something goes wrong with the equipment with somebody who didn't change the backup time, that patient gets exposed to 600 mass. What tech do you want to do your grandmother's X-ray? Hopefully you like your grandma. I mean, I'm hoping you guys like your grandma and you say, I picked the tech that uses 20 mass, not the one that just fried my grandma with 600 mass. But you see what I'm saying? So even if you're not good at math, you still can do stuff like that and say, okay, instead of 600 mass, if something goes wrong, and all it has to happen to you is one time to have that happen, and you will be like, oh my God, I am adjusting my backup timer for the rest of my life because I'm never going to expose somebody to 600 mass because I didn't pay attention and my equipment malfunctioned. That equipment malfunctioning is not on you, but that backup timer is on you. So it's supposed to be set to 150%. So all of you that were, good with math or even just okay with math and saw, oh, she picked 10 math, she picked something really simple for me. So what's half of 10? Half of 10 is 5. So 150% would be 15. Okay, so just, make it easy on yourself. I don't care about making it easy on yourself. I would rather you have just doubled that. And if something went wrong, that person got exposed to 20 mass versus if something went wrong and that person got exposed to 600 mass. Okay, and that's by law what those backup times have to be set to. That's the maximum, is that 600 mass. So that's actually should be pretty scary to you guys when you think about how low mass we use. And then depending on what part of the body is it that's getting exposed. Is that your child that they're doing an X-ray on? Is that your mom? Is that your dad? Is that your, brother, sister? Is that somebody you love that's getting exposed? Because our family's going to get X-rays too, so you just have to think about stuff like that. Okay, and then I'm going to go ahead and put this down so that you guys have it. I talked about it earlier. And P, which is just our turns ratio. And that is a part of what makes up. And the good news is whatever I put on this stays on it. So if you actually go and watch this again, you'll actually have these formulas. So I think it makes it helpful for you. And transformer law, being PS over BP equals NS NP. And so this voltage and the turns has a direct relationship, okay? So if it's a step-up transformer, the voltage is what gets stepped up. If it's a step down, the voltage is what gets stepped down. So on a step down transformer, the turns ratio will be a fraction. So less than a whole number, okay? So it'd be like 1/10. Okay? And if it's a step up, I should have put that was a step down, sorry. Step up, the number will always be more than 1. And in case you didn't notice, I have trouble walking and chewing gum. So something like that, where like a 500 to 1 instead of a 1 to 10, like that. So the second part of that is if I can solve for my voltage, and if you guys find some of these on your rad reviews and bring them, we'll go ahead and take the time to solve them. Okay. And this is the relationship, the what they call transformer. There you go. Thank you, Pilar. Yeah. This one is the transformer law's effect on current. Okay. And so usually what they have you do is you'll solve this first equation, and then you have to actually use your information from this or this. Doesn't matter which one you use. You'll still get the right answer and plug it in with this. So do you see how VS over VP equals IP over IS? Okay, so this shows you inverse, right? So you have to remember that this second part, so the current, whichever way you have the voltage plugged in, the current has to be opposite, okay? So if you leave it VS over VP, which I suggest, Bouchon, for whatever reason in his, he got all cute and he switched the voltage side and put current the same way, and I don't know, I just think it confuses people. I think leave equations alone, because people get so strung out on equations that it just stresses them. So just remember that current is going to be opposite, and then you'll be able to solve the secondary part of that, which will be solving for what your current would be at one part or the other. And usually it's asking what it'll be at the secondary, or it could say, this was supplied at secondary, and then you'll have these numbers plugged in and you're solving for primary. It doesn't matter. It's just remember that they're inverse of each other. Okay? Is everybody okay with this so far? Okay. I mean, there's not a whole bunch of everybody still here, in case you didn't notice, but there's a few more things that I want to make sure that that we talk about. Okay. I don't think I'm going to go into all the different generators. I think I might send you the information on those, and have you come back if you have problems with it. But just recognize that our worst equipment that we ever had was single phase half wave equipment. And when we had single phase half wave, that used the highest techniques and the longest exposure times, because they couldn't flip that negative side of the pulse up to the positive. So you only had one positive pulse per cycle. So there were only 60 positive pulses per second. So that, that definitely is a limiting factor there. So the techniques were the highest and the longest. When you move to full wave equipment, what happened was they were able to take that negative half cycle, and instead of just suppressing it, they were able to take it and flip it to the positive side. And when they flipped it to the positive side, what occurred there was you still had that 100% voltage ripple, because you still, let's see if I can do this for you. Draw a line. It's hard to draw with your mouse, I'm just going to say that. And you had your single phase half wave. It looked like this. Okay, I'm sorry. It's hard for me to draw with the mouse. And then, so you had X-rays being produced here. I'm trying to draw little plus signs in there. It's not working out real well for me. So the positive portion of the cycle, that's when you had X-rays being produced. So X-rays were only being produced half the time. But we always went from 0 to peak to 0, because they suppressed this part of the cycle in the half wave. So it was like it didn't exist anymore. So when they went to full wave, what they did was those negative half cycles got flipped onto the top and became positive. So now you doubled. So instead of being down here, it was flipped up to the positive side. So now I have X-rays being produced twice the time, right? So there's more X-rays being produced, so it will only take half the time to produce the same amount of X-rays. So a good thing, but I still have 0 to peak to 0 every time. So when I say I have 100% voltage ripple, that's what I mean, is that I'm always starting back off from that 0 and going to that peak and come back down to 0. So it affects the efficiency or the energy of the X-ray. So that's what you have to recognize from all of these, is the problem is with efficiency or with the actual overall energy. Because yes, I reach the peak voltage, but I'll only have a few X-rays that actually are produced at that peak voltage, and a lot more of them that are produced at the lower energy and lower voltages. Okay, so that's an important thing to recognize. So, oh, good. Okay, Pilar, glad it does. Okay, so then when we go into, so these, so say I had to use, I'm just going to put up here, this takes twice the time, twice exposure time. As this full wave would. So that's single phase half wave here, and this is single phase full wave here. So then when we go into 3-phase, so say here I had to use 50 mass for this one, I'd have to use 50 mass for this one as well, but it would only take half the time to produce that 50 mass, okay? So then when I go to 3-phase, 3-phase is actually pretty darn cool, because when I go to 3-phase, and again, pardon my drawing, because we all know Miss Ray can't draw. I can't even draw a straight line. I just proved that right now. Oh, shoot, sorry. I just erased the whole thing. Yay, I am multi-talented. All that because I couldn't draw a straight line, and I still can't. 3-phase. Well, good news is you'll be able to see that on the earlier portion of the video. So if you watch it again, you'll still see it. So 3-phase, what's happening is we're producing these waves over top of each other. And I almost did a halfway decent job until it fell apart. So what happens, you get the idea, right? Because you can look in the book and you'll see it done so much better than anything I'm doing here. But what happens is here is in every single cycle, I have, this is 3-phase 6 pulse, so every cycle I have the 6 pulses in there. Okay, so that's a wonderful thing, because that means at the end of 1 second, I have 360 pulses. Well, what's really awesome about this is because the pulses come in on top of each other, is that they never drop to 0, because there's always another pulse. If I drew 6 of them, you'd see, you know, we're overlapping even more like they do in the book, but I just couldn't draw it good enough. But it never allows the voltage to get down anywhere near 0. So there we say that equipment's 86 to 92% efficient, because the voltage ripple is only 14%. It's only dropping down just until that next pulse comes in right on top of it. So that's a much better piece of equipment, and it's much more efficient. What they say we lose our efficiency in is getting to, once we first hit that exposure, getting to that peak energy and the stopping at the end. Okay, so they call that initiation and extinction time. Okay, so say I was using 50 mass on my single phase equipment. On this equipment, I could drop my mass to half of that. So I could drop my mass to 25 mass. Or, and I want you to think about this because this is something that you want to know, but you should also know what is a better choice versus what is a worse choice for the patient. The other thing that you can do is you could reduce your KVP by 10. Okay, because since this is more efficient, it affects the energy of the X-ray. So our X-rays have more energy. Oh, well, that makes sense, right? Because the voltage never drops to zero. So I have that higher energy being sustained. Okay, and this should help you next week when we go into emission spectrum as well. And so dropping that KVP by 10 would not ever be a choice that I would make, because that just means I just increased that patient's dose pretty much by doubling it. So I basically kept the patient dose the same, going from single phase to three phase when, hello, the changes in equipment were all supposed to be about affecting a change in patient dose. So why would I want to adjust the KB down? That's not a good choice. But just recognize that you can, because you know that you can. But you need to know why you wouldn't want to either. Okay? And then the next thing is, if we had three-phase 12 pulse, instead of the 6 pulses per cycle that we had with the three-phase 6 pulse, now we have 12 pulses per cycle. Okay, so that's, we get the 12 pulses every 1/60th of a second, or 720 pulses per second. So this is like 96% efficient, and the voltage ripple's only 4%. Okay, so that's a wonderful thing, because it's almost there, right? It's almost at that top. So again, but when you go from, even though if I went from a three-phase 6 pulse room to a three-phase 12 pulse room, I would change my technique, because I'd know I can use a lower technique. Everything registry wise, they leave three-phase equipment at, if we're going from single phase to three phase, we're going to cut our technique in half. Okay, so you just want to know that for your three phase. But recognize, if you're working in a department and you have some three-phase 6 pulse and three-phase 12 pulse, that your technique should be lower in your three-phase 12 pulse room. Okay. But registry wise, again, you just want to know, if you were going from single phase full wave, that your technique would have dropped in half. So it would be that 25 mass, or dropping the KV 10. So then we go to high frequency. And most high frequency equipment is, it's actually pretty funny. It starts off with the single phase generators, because the three phase power is very expensive to run. So the cost of that equipment, the initial cost, is very high. And that's what keeps a lot of places from using three phase equipment. But if they have three-phase power, like at a hospital or whatever, then having that three-phase equipment is not, is not a huge big deal. But the initial cost is what's really bad with three-phase equipment. But now here's the nice thing is, I can have a little cheapy room like the one we have in room 1. And that little cheapy room is a single-phase equipment paired with a high voltage generator. Okay, so it doesn't cost a lot to do the initial power or anything for it because it's just using standard single phase power. So that's a benefit. It's low cost. But when it's paired with that high frequency generator, that high frequency generator works much different than any of the other generators, and it works with stacked pulses and stuff, and we're not going to go into all that detail, but just recognize it's the best thing we have out there. The voltage ripple is less than 1%, and it's 99% efficient. So it means basically I'm getting so many, because it looked like this. You go up and then you just have that little tiny bit of loss at the top, and I can't even draw it good, but you can look in your Bichon because it's all drawn out nice, but you just have just what you lose at extinction, at initiation and extinction is all the loss, and it's less than 1%. So for that, let me see, I don't want to make it where it's such a pain in the neck, but say that initial technique that we started with on our single phase equipment had been 60 mass. If I started with 60 mass and I moved to this single phase, move to the high frequency generator, then I could go from that 60 mass down to 20 mass because the high frequency generator requires only a third of the original technique. And let me see if it were. So should be, if we started with the 50 and I didn't get lazy and say I'm not even going to try to figure out what a third of that should be somewhere around 16.5 for what that would be if we just left it saying 50 and go to a third. But so anyway, so that's all the more you're doing there. I just got lazy and I was like, brain's not going to work to figure that out. But then I was like, I have a calculator, yay me. But basically your technique's going to be reduced to a third of from that original high frequency or single phase full wave equipment. So that being said, on this equipment, I could reduce my kV by 12 kV, or what would be about 16%. Okay, now again, why would I want to do that? Because that doesn't represent any patient dose reduction, and then that would mean that I was using that same initial mass, and shame on you. If you had single phase equipment, you were still using 50 mass for something that you could be using 16 mass for. I'd be like, what the hell are you doing? So wouldn't be a good choice. So does that make sense to you guys? The differences there?
Yes.
Okay. All right. So have I hit upon any questions that you have for me at this point? Or does your head merely feel like it wants to explode? Okay. Well, that's not a surprise that you don't have any now, because it's a lot to take in, and some of you might want to watch that more than once and come back with questions